So our 16-bit computer is starting to show some promise here. We have the instruction pointer, but more important than that is we have the memory address register here. What the CPU really wants right now is to load this address in memory, then we can decode the instruction. The only problem is we have no memory right now, so that's what we're going to do. We're going to build out the memory units. So let's try and build a full-fledged memory controller for 16-bit memory with read and write operations. So this is the RAM that we're dealing with. It's only 32K and not 64 because it's technically a 15-bit RAM stick. We have 15 address lines, and then we have 8 data lines. And we just choose whether we're writing to those addresses with this data, or if we're going to output from this address on these data lines. Relatively straightforward. So I'm going to control the address with these 2 dip switches, and we could turn on if we want value 1. That could be address 1. Turn on both of these, that's address 3, so on and so forth. Let us put some pull down resistors on here and then get some power going. So now we could just place the RAM here, and if we look at the layout again, then we can plug in the address lines here. So if we treat this as the least significant bit on this side going up like regular binary, we just need to connect bit 0 to address 0, and then 1, 2, 3, 4, and so forth. It's oriented like this. Here's the first 8 address lines going in, and now they start to bounce around a bit. So there's our address lines. For the addresses, I don't think it's very important for us to see the LEDs. It's a very straightforward connection. However, for the data lines, I do want to see the output. I'm probably going to try and put them here. So the data lines are right at the bottom of our chip, pretty much right down here and right down here. So I'm going to put bit 0 over on this side to bit 0 in the normal configuration. And I forgot to put VCC in, so I guess I should do that now. Well, this is actually ground. I need to remember that since it's upside down. Okay, ground should be in now. We have 0, 1, and 2 of our data lines. 3 through 7 is starting from the bottom here going up. Okay, so the idea here is that we have our addresses going into the RAM, and that works, and we have the data coming out of the RAM going into the LEDs so we could see the data that's on the RAM. However, we need to first be able to put something onto the RAM that we can then see it come out. I'm going to use another dip switch here, use pull downs on the output and connect VCC to the input. All right, these little guys are in. The most critical thing here is we want to write into the RAM at this address with this data, but we also want to read from the RAM with this address and this data, and we have one set of LEDs. So what we need to do is add a chip to filter our input pretty much to only allow it to output when we want it to do that. I'm going to use an LS245, a bus transceiver. So it's just a tri-state output that will allow us to essentially turn off the output from our input side when we want to read from the RAM, and allow the RAM to, without any contention, just freely output to the LEDs. Because if we turned on both of these, if they were both talking at the same time, I think there might be shorts or something. I'm still new to this, but I know that we need this to isolate when we want to write data and we want to read the RAM data. It doesn't interact over here and it goes straight out to the LEDs. So I'm going to park this guy right next door, and then the output of the dip switch, instead of going directly over here, we're going to go in here first, and then this will connect over there. And that way we can control when it's actually going to output or when it's just going to lock everything and not let any information come out of here. We can see there's 2 sides, A and B. One is input, one is output. We can choose a direction, and you see this output enable here. When we activate the output enable, then it will allow our data that comes in here to exit. But when we don't have output enable turned on, it will sort of lock this side, and any data that comes in here will just kind of die inside and not escape out. So let's connect our output here to our A side. So our data is now going into our transceiver, and now we can connect the transceiver itself to the LEDs here, basically going right in with these ones. So our data here will be connected to the RAM, and the RAM will be connected to the data, and both of them will be connected to the LEDs, and we'll just control who's outputting at what time because both of these have output enabled. Transceiver is connected now to our RAM because these guys are all connected together, right? Data comes out here and it can access here, but really we want to be able to write into the data through the gray lines, into the red and oranges, into the RAM. And then when we want to output from the RAM, we almost want to shut this guy off, as if we pull out the plugs, pretty much is what this guy will accomplish. So we virtually pull out the plugs, and then the RAM is able to speak very cleanly to the LEDs to show us what's inside the RAM. But we do need to get the control lines. I really should have done that first. So we need to plug in our VCC. We need our write enable to be button operated. We need our output enable to be button operated, and this guy needs to be pulled down. So VCC is this first slot, and then our write enable is right next to it. So white is going to be the write. All right, so at least we have some color coding here. Read and write. And then on this chip now, let's connect up A to B. So we need to connect this to VCC. Of course, this goes to ground, this goes to VCC, and then this guy also needs to be on a button. And I think that's it. So this is our output enable. All of these buttons that we're ultimately gonna have, they're active low. They need to be high by default. So we're gonna put pull-up resistors on each of these. I'm gonna use my 10Ks again, so that by default, there's high signals going on here. So all the chips are kind of like disabled. And then we'll use a button that grounds this connection so that it gets low. So when we press the button, it becomes low, and then this will output. Or when we press one of these low, then it will either read or write. Okay, so right now, these should have high levels by default. So he's not outputting, and he's also not reading. So he's just kind of idling. So we need a way to make these go low so that we can activate each individual chip. And we're going to use transistors for that. And then now we need our buttons. I think I have these transistors backwards actually. All right, I had to flip around one of these transistors, but we want the pull-up resistors to go on the collectors of them, and then the emitters to be grounded and the buttons to go into the bases. All right, similar thing here. We have our button that's being powered by a pull-up 1K, and then it goes into the transistor, into the base. So it should ground this wire when the button is pressed, and we can give it a shot. So if I press this, nothing should happen because we have no lines set up. If we turn on the least significant bit, the 1 bit, and it does seem to work. Turn on all of them. One of them, maybe I put the LED the wrong way, which I think I just skipped a cable, and one of them was in the chip select. So let's try this again. All on now, and I'm gonna turn some off. We can see them turning off one by one. Okay, so now what we have to do is we need to test saving. The way it should work is we basically hold this down to output. So let's say that we turn on, let's say value 101, which is a value of 5. So there's 101, that's 5. So the idea is that on this left side, we need to put in the address. I'm gonna turn on address value 1. So let's say that address 1 should be equal to 5101. So the way that this is wired up is we have our output data, like output immediate value. Then we have our read, which will read from memory, and we have our write. So we need to hold down our output, and then it should write, if I tap that, to this memory address. And if we read now the value at address 1, we do indeed have 101, which is pretty cool. Now what I'll do is I'm gonna turn on address value 2, bit 1 we could say. This is bit 0, so bit 1 is on, so that's the value of 2. So at address 2, let's say that we're going to have value 10, 1010, because 8-bit turned on and 2-bit turned on, that's 10. So let's make sure it looks like that, 1010. And now what I'm going to do is write. So I'm going to hit this button here, which should write it to address 2. I'm going to turn off these bits just to reset. And then now if we try to read at value 2, we get 1010. If we turn this back to address 1, then we still have 101, which is 5. So this seems to be working very well. So this is a manual 16-bit memory controller. The idea is that our computer over here is going to have to integrate with this. Ideally, what would happen is this address here would go into our current manual address, output the data, and then we can decode it. We were fortunate enough to test it with the Arduino, which is why I think it was such a straightforward operation. Basically just replacing the Arduino with these manual inputs with the 245 and the address line. So not too much of a difference, but it is really cool to see it working only through circuitry where we're able to save 32,000 bytes pretty much. Next up, what we need to do is configure this so that we can take our instruction memory address register and pull out the value that was in here. And then we can start decoding, and then we can really start executing, hopefully. But yeah, so thanks for joining me. This has been really fun. I'll see you soon when we continue working on this project. Thanks for watching.